The ABC of the Universe. The BBC presents the second talk in a series of 7 by British astronomers. Today's talk is called The Birth, Life and Death of a Star and is given by Dr Vincent Reddish of Jodrell Bank.
What is a star? The easiest one to study is our own sun, so let's start with that. It's a sphere of hot gas more than 1,000,000 kilometres or 800,000 miles across. 3/4 of its mass is hydrogen and almost 1/4 helium, the next lightest gas. All the other elements together account for only 1% of it. The temperature of the surface is nearly 6,000 degrees centigrade, and it is far hotter than that inside, where the great heat causes such violent agitation and collisions between the particles of matter that all the substances are broken into separate atoms. Even the lead, the iron, the gold are in the form of atomic gases. But the sun is so massive, the self-attraction of its own gravitation is so strong, that the gas inside is compressed until it is denser than water. We can't see into the heart of the sun, but we can study what goes on there. We can measure the amount of light and heat that falls on 1 square metre of the surface of the earth. Knowing how far the earth is from the sun, we can go on to calculate the total amount of heat pouring out of the sun in all directions. Heat only flows from hot regions to colder ones, so because heat flows out of the sun, the centre must be hotter than the surface. The bigger the difference in temperature, the faster the flow of heat, and the temperature difference necessary to account for the measured outflow of heat from the sun has been determined. It turns out that the temperature at the centre is about 13 million degrees centigrade. At this temperature, the nuclei of the atoms of hydrogen collide with such violence that they fuse together to form helium atoms, giving off a tremendous amount of energy in the process. In fact, the centre of the sun is a vast nuclear reactor, supplying the energy radiated and transmuting hydrogen into helium. Now let's leave the sun for the moment and look at some other stars. There are plenty to choose from, for by using large telescopes with photographic plates or photoelectric cells to measure the tiny amounts of light collected, the brightnesses of stars 1,000,000 times fainter than those visible to the naked eye alone can be measured. Besides brightness, the distances to many of the nearer stars have been measured. The nearest ones are several 100,000 times as far away as the sun, and they are separated from each other by similar distances. Between the stars lie clouds of gas, mostly hydrogen, 1,000,000,000,000,000 times more rarefied than our atmosphere, but of such vast extent that they still contain enough mass to make millions of suns. When we know how bright a star looks and how far away it is, we can work out how bright it would be if it was brought as close as the sun. This has been done for many stars, and the brightnesses are found to cover an enormous range, from as little as 1/1,000,000th to as much as 1,000,000 times that of the sun. But stars vary in colour as well as in brightness, and the colour of a star gives us a measure of its surface temperature. It tells us whether it's red hot, white hot or blue hot, and more accurate measurements of the colours lead to correspondingly precise estimates of the surface temperatures. We find that most of them are between 2,000 and 20,000 degrees. So the colour tells us the temperature, and the temperature, rather surprisingly, helps to tell us how big the star is. The amount of surface area which a star must possess to radiate the amount of energy it does when heated to the measured temperature can be calculated. From this area, the size is easily deduced. We find that some stars, the white dwarfs, are as small as the Earth, with a ton of matter squeezed into each cubic centimetre, and some, the red giants, are larger than the diameter of the Earth's orbit. But most stars are neither less than 1/10 of the diameter of the sun, nor more than 10 times it. This majority falls into clearly defined ranges of brightness and colour, and we call them main sequence stars. So much for size and brightness, but we also want to know how much matter stars contain. This is where double stars are useful. Some stars occur in pairs, revolving around each other. Their distances apart and the times of revolution have been patiently measured. Just as the mass of the sun can be found from knowing the pull of gravity that's needed to keep the Earth in its measured orbit, so the masses of these double stars can be found from the observations of their orbits. In this way, we found that the masses of stars lie in the range from about 1/10 to 100 times the mass of the Sun. Going back to our own Sun for a moment, we've now got far enough to see that in all its properties, size and mass, brightness and temperature, it's an average main sequence star. The next thing is to see what such a typical star is made of, and we do this by studying its light in more detail, by splitting it up into its component colours with a glass prism or a diffraction grating, and photographing the resulting spectrum. The result is something like a rainbow, which is a crude spectrum of the Sun. But in an astronomical spectrograph, the light from a star can be spread out so that each colour is itself subdivided into 1,000 shades, and the brightness of each shade can be compared to the next. These spectra of the stars turn out to be crossed by many narrow dark lines, produced by different kinds of atoms in the star. Each kind of atom produces a distinctive pattern of the absorption lines, and the more atoms there are, the darker the lines. Thus the kinds of atoms in the star and their abundances can be determined from examining the spectrum. In this way, it has been found that in the stars, as in the Sun, hydrogen is much the most abundant element, and helium the next most abundant. The combined amount of all the other elements, which we call the heavy elements because their atoms are heavier than those of hydrogen and helium, varies from star to star, from almost nothing to a maximum of only about 2%. But stars don't only differ from each other, they also change throughout their lives and are very different at the end from what they were at the start, and it is important to study their aging. The principle involved is simple. Suppose that we know the total amount of energy that a star can produce. We measure the rate at which it is radiating this energy in the form of heat and light, and we can then calculate how long the energy supply will last. This is the expected lifetime of the star. In order to find out its age, all we then need to know is what fraction of the energy supply has already been used up. Take the Sun, for example. The rate at which it is radiating heat and light energy has been measured. Its major source of energy comes from the nuclear reactions which convert hydrogen into helium. Nuclear physics tells us how much energy is produced when 1 gram of hydrogen is changed into 1 gram of helium. The mass of hydrogen in the Sun is known, and therefore the amount of energy which the Sun could produce by converting all its hydrogen into helium can be determined. At the present rate of radiation, there is enough to last for 100,000 million years. But the rate of radiation won't remain at its present value. When we look into the way in which the interior structure of a star alters with time, we find that when the central core of hydrogen, a few tenths of the total hydrogen, has been consumed, the star begins to change comparatively quickly. It grows larger and larger, brighter and brighter. It becomes a red giant, 100 times as large and 100 times as bright as it was. The remainder of its hydrogen is soon used up at such a high rate. In this way, our own Sun is due to begin to change into a red giant when it is about 10,000 million years old. It has already completed about half its life. The most fruitful use of these ideas about age has been in applying them to clusters of stars. A cluster may contain from 100 to 1,000,000 stars, each unable to escape from the gravitational pull of the others, all formed at about the same time from a single large cloud of gas, and so having a common age and composition, but varying widely in their individual masses. Now the measurements of double stars I mentioned earlier have shown that the brightness of a star depends very strongly on its mass. An average star, a main sequence star, with twice the mass of the Sun, is 10 times as bright. So although it has twice as much nuclear fuel, it is using it up 10 times as fast. Therefore it can only last for 1/5 as long as the Sun, 2,000 million years, before it becomes a red giant. So if we observe that in some particular cluster all stars more than 10 times as bright as the Sun have become red giants, then we can say that the cluster is 2,000 million years old. If stars as faint as the Sun have become red giants, the cluster is 10,000 million years old, and in this way the ages of many clusters have been found, ranging from a few million to 15,000 million years. Although we are still faced with many unsolved problems, the major features of the birth, life and death of a star can be pieced together to form a consistent story. The story begins 15,000 million years ago with a large diffuse cloud of pure hydrogen gas, 100,000 million times as massive as the Sun, a million miles across. This was the cloud out of which all the stars in our galaxy, including the Sun, ultimately formed. The first stars to form contained only hydrogen gas. Suppose we follow the evolution of one of the more massive of them. It begins as a large, diffuse, cool fragment of a gas cloud. The fragment, some 30 times as massive as the Sun, contracts slowly under the attraction of its own gravitation. As the gas atoms fall inwards, they gain speed, sharing the energy amongst each other in collisions. This energy of motion is heat. Thus the star heats up as it contracts. Hotter and hotter, the center reaches 1 million, 10 million, 20 million degrees. Suddenly, as this high temperature is reached 60,000 years after contraction began, nuclear synthesis begins to convert the hydrogen into helium. This supplies the energy needs of the star for the next 6 million years. During this time, the appearance changes little because contraction is prevented by the heat produced at the center. But when the inner 60% of the hydrogen has been consumed, the star becomes a red giant. The outer regions expand to enormous size, but the inner core contracts, again becoming hotter and hotter. 100, 200 million degrees. More violent nuclear reactions convert the helium into carbon, oxygen, and neon. Hotter still, 600 million degrees, and magnesium forms from the neon. 1,500 million degrees, silicon, aluminium, calcium. 2,000 million degrees and still rising, iron, nickel, chromium, and other metals, heavy elements, are now being formed in the nuclear reactor in the heart of the star. Suddenly, the nuclear reactions become unstable. The star collapses and then violently explodes, blowing the elements out of the intensely hot core, out into space at thousands of kilometers a second, into the clouds of pure hydrogen gas. All that remains of the star is a faint white dwarf. 100 million years after stars first began to form from the gas cloud, 3% of the gas had condensed into stars. Millions of stars had exploded, and already the gas clouds contained 1/100% of heavy elements. After 10,000 million years, 9/10 of the gas had condensed into stars. The remaining gas was made up of 3 parts hydrogen, nearly 1 part helium, and 1% heavy elements, and it was at that time, 5,000 million years ago, that the Sun and the planets were formed from it. And although hydrogen gas is still the most abundant element in the galaxy by far, the things with which we are familiar in everyday life are largely made out of that 1% of heavy elements. The land and sea, the rocks and trees, our food and our machines, even we ourselves, are made out of atoms once forged in the nuclear furnaces at the centers of stars.
The Birth, Life and Death of a Star was the second talk in the BBC series The ABC of the Universe. It was given by Dr Vincent Reddish of Jodrell Bank.